Okay, I think we can start our session. This session is dedicated to refrigeration, reciprocating compressors, part 2. We had another session before. We should have 4 papers in this slot talking about reciprocating machines. Let me introduce myself. I'm Marek Zgliczyński. I'm R&D Director in Embraco North America. Embraco is part of the bigger group Nidec Global Appliance, and is, let me say, one of the sponsors of this conference. It's a long time since Embraco has a factory in Slovakia, so we have a pleasure to sponsor this conference since the beginning. And I think it's very important event for the region. And we fortunately were not able to be there personally. That is always quite interesting experience. But I hope the next conference will be done in Slovakia, like it was in 2017, where everyone can meet personally and enjoy nice events that was normally coming with the conference participation. Okay, so I'm co-chairing this session with Tiago Dutra, that led the previous part of the reciprocating compressors presentations. So, and he will be also the first presenter of this session. Tiago is the PhD, I think, professor. You are teaching in Polo Institute, that is specific institute dedicated to refrigeration in Santa Catarina University in Florianopolis. Extremely nice place to visit and to stay. And he has also, I think, quite important industrial experience, being one of the Embraco, let me say, members in the past. Okay, so and I think he was working on the product that is also the subject of his presentation, that is the linear oil-free compressor. The title of the presentation is the numerical analysis of the transient compressible fluid flow in the piston cylinder clearance of the oil-free linear compressor. And this paper was let me say, written together with Claudio Santos and Professor Deschamps, I think both from Santa Catarina University from Polo. So Tiago, the floor is yours now for your presentation. So we can start with the presentation.
Thank you, Mr. Chairman, for the introduction. This presentation is divided in 5 topics: introduction, simulation model, analysis of thermodynamic inefficiencies, results, and conclusion. Linear compressors are driven by a linear actuator coupled to a resonant spring and a magnet motor. In these compressors, there are low side loads and few moving parts, which allow oil-free operation. This oil-free operation brings some advantages, as the increase in the heat exchanger's effectiveness and reduction in friction moving parts. However, the effect of the aerostatic bearing formed by the piston cylinder clearance on the compressor efficiency is not yet fully understood, and this is the main motivation of this work. Thus, the main objective of this work is to assess the thermodynamic inefficiencies brought about by the transient compressible fluid flow in the piston cylinder clearance of an oil-free linear compressor. And to achieve this main objective, we have to achieve 3 other specific objectives, which is to develop a numerical model to perform the simulations, to identify and to quantify the different sources of volumetric and isentropic inefficiencies for a baseline operating condition, and after that, to carry out a sensitivity analysis to evaluate the effect of design parameters on these inefficiencies. The simulation model is given by a combination of three submodels. One, the compression chamber model in this region. Two, the piston cylinder clearance model in this blue region. And three, the restrictor channel model in this red region. The compression chamber model, herein referred as CC, is based on mass and energy conservation equations applied to the control volume shown here. And it follows an unsteady state integral formulation. The pressure drop through the valves, suction and discharge valves, and mufflers are disregarded, as well as the in-cylinder heat transfer. The CC model computes the pressure and temperature in the control volume, as well as the mass flow rate through the suction and discharge ports, and the power consumption to compress the gas. The mass flow rate through the clearance is computed with the PCC model. The piston cylinder clearance model, called PCC, is based on a 3D finite volume method applied to the piston cylinder clearance, represented by this blue region, to solve the transient compressible fluid flow. The radial clearance is unfolded and the geometry is transformed in the geometry that is seen in this figure here. A further simplification is adopted due to the symmetry associated with the circumferential direction. The PCC model boundary conditions are pressure and temperature supplied from the CC model at the compression chamber interface, no-slip wall and fixed temperature at the cylinder surface and piston surface, mass flow rate computed from the RC model at the restriction channels interface, symmetry, and evaporating pressure and suction temperature at the internal environment surface, located at the skirt gap of the piston cylinder clearance. The mesh size is approximately 46,000 elements. The restrictor channel model, RC, is adopted for solving the laminar isothermal compressible fluid flow in the restrictor channels. These restrictor channels are helical grooves positioned on the outer surface of the cylinder. The gas flows through these channels until reaching the feeding orifices that communicate the channels with the gap, the piston cylinder clearance. The model is based on Hughes and Pratt 2016 for computing the mass flow rate in these channels. Analysis of thermodynamic inefficiencies. The thermodynamic inefficiencies are divided in two main groups: the volumetric inefficiency and the isentropic inefficiency. Let's take a look to this schematic here that shows the energy and mass flow interaction between submodels. The mass flow rate comes from the evaporator and flows through the suction line to reach the compressor. As it gets to the compressor, it flows through the suction chamber and then goes to the compression chamber, where the mass is compressed and then released to the discharge chamber. After that, it flows through the discharge line until reaching the condenser. Part of the mass that is compressed in the compression chamber leaks through the piston cylinder clearance and then recirculates, coming to the suction chamber and then again to the compression chamber. Also, part of the mass that is compressed in the compression chamber is delivered to the discharge chamber and then comes back to the piston cylinder clearance by flowing through the restrictor channels. This is for the purpose of aerostatic bearings. The actual mass flow rate at suction line is computed from the theoretical mass flow rate minus the volumetric losses that are broken down as follows. This first term is due to the dead volume effect, the second and the third term are due to the return of mass in the top gap. This term is due to an increase of the gas density that enters the compression chamber, and this term is due to the recirculation of mass inside the compressor. As we divide this expression by the theoretical mass flow rate, we obtain this expression right here, where these terms are specific volumetric inefficiencies. An energy balance applied to the compressor control volume gives this expression, where this power represents the compression power, and this represents the piston friction power. These two terms here are energy rates associated with the mass flow rate at the inlet and outlet of the compressor. This term is the heat transfer rate at the piston cylinder clearance. And these two remaining terms are heat transfer rates at the suction and discharge chambers. These heat transfer rates are necessary to keep the entropy constant along all the compressor path and are computed from these two energy balances here. As we divide this equation 2 by the isentropic power, we obtain this expression where these terms are isentropic inefficiencies. Results. We will present the results for the baseline operating condition, which is given by the establishment of these parameters here. First of all, we will present the results for volumetric inefficiency. As we look to this table, we realize that there is a reduction of 54% in the volumetric efficiency associated with the dead volume effect, since we have a small piston amplitude in this operating condition. Additionally, the volumetric inefficiency associated with the piston cylinder clearance is only 0.79%. And from this loss, we realize that leakage through the top gap is the most important inefficiency, which reduces the amount of mass that flows from the suction port to the compression chamber. Regarding the isentropic inefficiency, we observe that the effect of the piston friction is small when compared to the leakage through the piston cylinder clearance on the isentropic efficiency. We also observe that the isentropic inefficiency in the gap is the main source of inefficiency. Finally, we computed the viscous dissipation rate along the clearance volume and obtained an integrated value of 0.69 watts. This value represents 75% of the energy that enters the gap during the compression cycle, which is 0.92 watts. This result indicates that the viscous dissipation rate plays a major role on the isentropic inefficiency. Parametric analysis. Due to time restrictions, I will only present results for the effect of the radial clearance. So as the radial clearance increases from 2.5 to 10 micrometers, we observe that the volumetric inefficiencies associated with the leakage at the top clearance during the expansion and suction strokes increase. And the volumetric inefficiency due to the leakage at the skirt gap increases even more, as we see here, due to increasing the top gap leakage. Finally, the volumetric efficiency decreases 2.5%. The same variation in the radial clearance leads to a decrease of the piston friction power. However, we observe an increase of the isentropic inefficiencies related to the gap and to the suction, as we see here, leading to a decrease of 4.2% in the isentropic efficiency. Conclusion. A convenient method was adopted to quantify losses in the piston cylinder clearance of an oil-free linear compressor. The leakage from the top gap to the compression chamber along expansion and suction strokes was found to considerably reduce the amount of mass of refrigerant that enters the compression chamber through the suction valve. The mechanical energy dissipated by viscous friction in the clearance is the most influential source of isentropic inefficiency. And as the radial clearance is varied from 2.5 micrometers to 10 micrometers, the volumetric and isentropic efficiencies are decreased in 2.5% and 4.2% respectively. Finally, I would like to thank all of our partners and to thank you for your attention.
Okay, thank you, Tiago, for the interesting presentation. We have now time, I think, for at least one question from the audience, if anything appears on Slido. For the moment, no. So I have one question here. Okay. You can see me or not?
No.
Okay.
Now yes.
No, because the my question is the following. You know, this linear compressor is not only used in vertical position but also horizontal. What is the influence of the gravity, of the weight of the components on the clearance behavior in this kind of linear compressor?
We should not have too much influence on that. That's why this compressor is also can be used in different positions, right?
Because without lubricant, this is what is expected, basically. No?
Yes, yes. We in our solution here, we did not take into account the gravity force in the solution, right? So I cannot give you an answer precisely, but I would not expect too much variation on that.
Okay, thank you. Now we have the first question here. The discharge muffler, is the discharge muffler connected with cylinder gap? Does it allow backflow from muffler to the gap?
The discharge muffler, actually, it's not solved. This is only an energy balance that is applied in a discharge ambient, we'll say like that, to account an energy amount, so as to quantify the effect on the isentropic efficiency. But actually, the model, there is no muffler at all. So we only compute the mass flow through the, but let me just see the question again. The discharge muffler connect with the cylinder gap. So we do not have a discharge muffler.
Yeah, I think it's not connected. No?
Yeah, it's not connected, but we have a mass flow from the discharge environment that feeds the restrictor channel. And this is computed from the gap model.
Exactly. And here is the, I think, interesting question from Peter Nexa. How the efficiency of this compressor compared with the standard compressor with lubricant of the same capacity?
This I would say that would be maybe 10% more efficient or something like that. I would say, but yeah, because there is a decrease on the mechanical efficiency, the mechanical inefficiency. So the bearing is much more efficient, and also the electric motor that used, and also the effect of to spend or to take the kinetic energy of the system in the motion of the piston. So the power consumption to compress the gas is much lower as we spend a part of the kinetic energy using the resonance of the system. So
okay, thank you, Tiago. We have now to move to the next presentation. The next presenter is Asmund Ervik from Norway. He is the PhD of Norway University of Science and Technology, and is presently a research scientist in SINTEF. SINTEF, that is the institution with very long tradition in working on natural refrigerant, particularly on CO2 ammonia. And I think his paper, the title is Modeling of Dynamics of Ring Plate Valves in Reciprocating Compressor using Couplet CFD FEM Simulations. So please, Asmund, make your presentation. I think it's recorded one again, so we will be talking with the questions after the presentation.
Good afternoon, everyone, and thank you for attending this talk on modeling the dynamics of ring plate valves in reciprocating compressors using coupled CFD FEM simulations. My name is Åsmund Ervik. This work is a collaboration between SINTEF Energy Research, where I work, and SINTEF Industry, both of us located in Trondheim, Norway, and the Maekawa Manufacturing Company in Japan. And we have collaborators from all three companies who have contributed to this work. The outline of my talk is as follows. I will give a brief introduction to valve dynamics in compressors. We will present results from experimental observations in real compressors. Then I will talk about the CFD modeling and FEM modeling of the valve system, and then about coupled CFD FEM simulations. Finally, I will discuss and make some conclusions. So the compressor, as you know, is used to drive refrigeration systems. And in particular for reciprocating compressors, it is necessary to have valves that control the flow of gas. And this valve design has a major influence on the efficiency and the reliability of the compressor. So if we look in a typical compression cycle, starting at top dead center, the piston is traveling down, the gas pressure inside the cylinder decreases until the suction valve opens. The suction valve then lets fresh gas enter the cylinder space until the piston reaches bottom dead center. The suction valve closes and the compression stroke starts, where gas is compressed until the pressure reaches the desired level. Then the discharge valve opens and gas flows out of the discharge valve into the discharge plenum. In the figure here is a Maekawa M-series compressor, which has a suction port, cylinders and pistons, suction valves located here, which suck gas, and discharge valves located here, which discharge the gas into the discharge port. These discharge valves are ring plate valves, and in a simplified illustration they appear like this. We have the blue surface, which is the ring plate that can move up and down. At the bottom is a valve seat. At the top is a valve cage. Springs act on the ring plate to close it against the gas pressure. When pressure is high enough in the cylinder, the ring plate moves up and gas is discharged. Experimental observations in real compressors were made by Maekawa at the Moria plant test facility. So the M-series compressor, as shown in the figure, was instrumented, running with ammonia refrigerant at real conditions, and the displacement of the valve ring was measured using eddy current sensors, while pressure was measured in the cylinder and discharge chamber. These are the results from that observation. This is one full stroke, so TDC to TDC. So we have the same behavior. The pressure in the cylinder decreases when the piston starts traveling down until the suction valve opens. Gas is sucked into the cylinder. Then the suction valve closes, the compression starts. And here we can see the discharge valve opens. And the discharge valve in this case opens quickly, reaches the maximum, and stays open for some time until it closes more smoothly. And these are three curves illustrating points on different places around the ring. And that these curves overlap illustrate that the valve is flat throughout the motion in this case. So this data, and particularly the pressure data, is used as input for the modeling. For CFD modeling, solve the Navier-Stokes equations for gas flow with a moving mesh to implement the valve ring motion. These are the conservation equations for mass, momentum, and energy, which are discretized using a finite volume method. The domain looks like this, with an inlet in blue and outlets in red. The ring plate is represented as a hole in the mesh, and a dynamic mesh solver is used such that this can move up and down. For this, a custom OpenFOAM solver has been developed. We employ the Peng-Robinson equation of state and use properties corresponding to ammonia gas. The valve ring moves according to the combination of total aerodynamic forces from the gas, spring forces with preload, and a simplified model for the impact between the ring and the cage. These are the results of CFD simulation of a single valve cycle, with snapshots going in this sequence. In these figures, the red color indicates a high pressure, while the blue indicates a low pressure, and the arrows indicate the velocity of the gas. We can see between the second and third frame that the valve has impacted the cage, and after this impact, a low pressure region is found above the ring. This contributes to the damping of the impact as a gas effect. Between the fourth and fifth snapshots, we have a similar impact with a similar damping effect. These figures also highlight the great benefit of using CFD modeling, that the pressure field can be accessed at all points in the domain, where experimental measurements would be extremely difficult, such as in the region between the cage and the ring. For FEM modeling, we have implemented a 3D shell element model in the LS-DYNA software. This includes a deformable valve ring, rigid valve cage, and plate. Springs are included explicitly, and friction is neglected. We analyze in detail the position of the valve ring, and we study also the effect of asymmetric aerodynamic forces. These are results from the FEM. On the top, this is a reference case where there is no damping added in the FEM. And we see that this leads to a strong bounce after impact. Since this impact is purely elastic, the energy is conserved before and after impact. The real system does not display this behavior, and this tells us that strong damping forces are present in the real situation. At the bottom, we see what happens when we apply asymmetric aerodynamic forces. In this case, the pressure is varied from the left to the right on the ring, with a magnitude of 10% variation. During the first part of the motion, a very small tilt is caused by this pressure imbalance, almost too small to see. But the impact amplifies this into a strong tumbling motion, which is undesired. This shows that even though the initial tilt by an imbalance in gas pressure is very low due to the high moment of inertia of the ring, the impact will amplify strongly any such imbalance, so it is important to avoid it. In the previous slide, the FEM results which I showed were obtained using experimentally measured pressures as the boundary conditions in the FEM. Now, since the pressures measured in experiments are not exactly at the location of the valve, this leads to a discrepancy. And to improve on that, we have developed loosely coupled CFD-FEM modeling. So using the pressure field computed from the CFD, still without including any explicit damping in the FEM model, we obtain a reduction in the bounce which we saw earlier. So in the bottom here, you can see what happens when we use the experimental data. This is the same as I showed previously, with a strong bounce. And when we use instead CFD pressures, which includes the damping effect of pressure above the ring, the magnitude of the bounce is reduced by approximately 25%. This includes that the gas pressure effects account for about a quarter of the total damping. The remaining damping is due to energy dissipated in the solids during impact, such as energy which goes into the cage. This is neglected in the current model. So we have employed experimental observations, CFD, and FEM modeling to investigate the ring plate valve dynamics. Our present models can account for the key phenomena in this system. We show that around 25% of total damping comes from gas dynamics. The remaining damping comes from the solid interactions and needs specific submodels. We also show that it is possible to resolve the detailed motion of the valve system. This coupling of CFD and FEM has provided new insights. But as always, there is more work needed to investigate the details of the valve system. Thank you for listening to the talk, and we want to acknowledge the financial support of the FME HIF Center. Thank you.
Thank you, Asmund. Interesting presentation. Personally, I have some confusion in terminology because we are in the small compressor world. We have much more simple arrangement of the valving. So my question is this, let me see, springs, those springs closing the discharge valve are touching directly the valve ring?
Yes, that is correct. They are touching directly the valve ring surface and pushing the valve closed.
So they have some additional dynamic effect on the mass and behavior of the valve, correct? Is this taken into account?
That is exactly correct. And in the FEM model, we explicitly model the springs with their mass and stiffness. Mm-hmm. So this represents an added mass
to the
for
system.
The ring.
Yeah. Okay. Yeah. Good. Uh-huh. And this cage is basically fixed. It's not moving part.
Exactly.
Mm-hmm. And the suction valve is more or less the same arrangement of the discharge valve?
Yes, it is. It is quite similar. It is built with springs and rings. Yeah.
Mm-hmm. Okay. Just curiosity. Do we have other questions? I think yes. Let me see there. No, I don't see any question coming for us. So, Tiago, maybe you have any question since you are more expert in these details.
You're muted. You're muted, Tiago.
Okay, now I'm okay here. I don't know if maybe I didn't realize in your presentation or maybe in the paper. But I don't think you made a direct comparison between experimental and numerical results, did you?
We don't. No, in this paper we don't show a direct comparison. What we show is that you have you have several factors that contribute to the damping of the impact, and we have analyzed in this paper the situation where you don't put any damping submodels in your FEM, and then we see a situation which is quite different between model and experiments. And to make the two match, you basically just tune a damping coefficient in your FEM, and then you get the correct behavior. But we don't show it in the paper.
Because when I look, no, sorry, Marek.
No, because I was saying there was two figures, figure 8 and 9 in the paper that I cannot find in the paper. So maybe this was making this.
Something that I was looking in the paper, that if you look to the experimental results, the valve displacement, the discharge valve displacement, you see that there is a peak. The peaks happens in the valve opens really fast, and after that the valve goes down, but we do not have a second peak, right? But in the numerical results we see that.
Yeah, it is. I mean, it's because we don't in the results that we show here, we don't include any damping in the solid impact. And if you include that damping in the solid impact, it goes up and then it has a very small bounce, and then it stays close to open and then it closes. So if you include that, then it matches very nicely.
Okay, thank you very much. We have to go to the next paper because we are behind the schedule. And the other questions that are coming, you can answer maybe later, Asmund. So thank you very much again. The next presentation is from Paulo Martins. He is the PhD in mechanical engineering, currently acoustic engineer in SICOP, Austria. So he will talk about, let me say, quite interesting topic that is, let me say, in the hands of all compressor manufacturers, how to optimize the suction muffler in order to reduce the noise emission of the product, especially in the, I think, in all size of compressor. That this is the issue. But here is a very interesting subject because it's studying the suction muffler design, considering, so compressor muffler design considering fluids and structure interaction. So Paulo, if you, I think we have the recording of your speech, so please go ahead with the recording.
Hello everyone, my name is Paulo Martins and I work for SECOP Austria, and today I'm going to show you our research named Compressor Muffler Design Considering Fluid Structure Interaction. This presentation is divided as a quick overview about our company and the objectives and motivation for this research, the methodology used for it, and then I'm going to go into more detail regarding the standard simulation that we used before, and of course about the core of this presentation, which is the FSI simulation, and of course the experimental results that we got out of it, and then the conclusions. So SECOP is an international provider of refrigeration solutions. We sell hermetic compressors and controllers for compressors, and our markets are light commercial, battery-driven, DC-powered mobile applications, as well as some selected residential applications. We are present on US, Europe, and China. And the main objective of this research was to improve the process of muffler design and optimization with a more sophisticated model. So the approach that we used was on optimization of a finite element model, considering the fluid structure interaction and then we performed also the experimental validation of these results. And the motivation for this was that our compressor mufflers are often made of light polymeric materials, and their interactions with the fluid inside the cavity and lots of pulsations and high pressures, sometimes it's significantly linked to the fluid structure interaction, and this may also be often overlooked. And of course, the muffler design must be robust enough to cover all of these critical bands while we are talking about noise. In this case, the acoustic cavity and also the valve frequency as well. So still in motivation, this is a spectrum of one of our compressors, and as you can see, the main noise is coming from the critical cavity bands from 2 kilo to 1.15 kilohertz, one-third octave band, and we should have two options here. One would be to tackle the cavity band. We should change the behavior of the cavity by changing the shell, which is nonsense because it's lots of cost into the project. Or we could think about the plastic side, which is only a suction muffler and can be 3D printed for prototyping and so on. So we tackle the problem by the suction muffler side, which is more efficient and much less costly. So the methodology for this research was first, back in the past, we used the standard acoustic finite element model. So we continue using it, considering the rigid walls and performing an heuristic optimization by tuning on the critical frequencies of the R cavity. But then we saw that it was ineffective, so we applied a new model considering flexible walls, and we performed the same heuristic optimization. And then we tried to put both of the mufflers inside a compressor and experiment with them and see the outcomes on the noise levels by the compressor itself. So our simulation workflow for the standard approach with rigid walls goes like this. We need an acoustic finite element volume of the suction muffler, which we can prescribe the properties of the refrigerant at a given temperature. And as boundary conditions, we only need the surface velocity on the inlet port and an anechoic radiation on the outlet port. And then ANSYS software calculates the input power and output power and can give us a post-process transmission loss. And this transmission loss is what we use as a parameter to try to tune and change the behavior of our muffler. So this is one typical transmission loss curve, and breaking it down to simple terms, when we optimize the suction muffler, we are looking into these high transmission losses here, and we change its shape to try to shift it back and forth to match the same critical bands on our compressor, so we can filter them out. And we take care about these anti-peaks, which are the lack of filtering by the suction muffler at all. So we need to avoid it to match one of those critical frequencies to avoid the noise problems. And then when we are comfortable with the optimization in between the simulation, we 3D print suction muffler, and we assemble a compressor with it, and we put it to test. For putting it to test, we need to ensure the same second of conditions of suction and evaporation side, and the same shell temperature of the compressor and the same room temperature, and we also monitor the running speed in order to guarantee the same repeatability between the results. And the outcome of this is the sound pressure that we can calculate the sound power level of the compressor, and we can compare the same compressor with different suction mufflers, and we have a better idea of if our our suction muffler is performing what it's intended to do or not. So these are the first experimental results that we obtained. On the left-hand side, you can see the results for low back pressure of the compressor, and on the right-hand side, the medium back pressure. The black lines are the compressor with the current muffler that we have without any optimizations at all, and the blue lines are the suction muffler optimized using the standard approach. For lack of better words, you can see that we failed. It was not very good, and we tried lots of different models by using the same standard approach, but we kept getting the similar outcomes of even increasing the noise on the bands that we should decrease the noise. So we start thinking, okay, this is not going very well. The model that we are trying to optimize is not representing the reality at all. So we need something better. And that's why we tried to do with the fluid structure interaction approach, the optimization by using it. And we added, of course, the walls of the suction muffler, and we also had to add the polymeric properties of it, and also add one more boundary conditions of where the fixations should be, which are highlighted in blue on the right figures, on the figures on the right here. And the same output parameters and the same post-processing was expected in order for us to compare the same transmission losses between the two approaches. So this was no surprise at all that these different approaches would give us very different results. As you can see here, the full lines were our standard approach, while the dashed lines is now our flexible walls approach using fluid structure interaction. And as you can see right from the scratch, you can see that some of the frequencies that we were trying to optimize there were already shifted, and some of the highest transmission losses peaks, they were decreased to the point that they didn't appear at all. And most importantly, some anti-peaks also appeared. And these anti-peaks are very important. They are very important because they show a very different behavior of the suction muffler itself, not coming only from the inner parts that we needed to tune before, but now coming from the suction muffler walls themselves, that we need to be aware when we are trying to create volumes and increase or decrease length of the pipes inside, because sometimes the muffler walls itself, they can be exciting the cavity range, and this is very bad for us. So this insight here was really important while trying to optimize our sub. And here I'm bringing the experimental results comparing the three mufflers. Um, the black lines are the current mufflers that we have in the market. The blue lines are the first attempt of optimization, and the green lines are the optimization using the fluid structure interaction. And as we can see, we were highly successful into optimizing it by using this more complex model. We achieved what we were intended to do by decreasing the noise in these critical bands a lot. If you look at the medium back pressure, we decreased the total noise of the compressor in almost 5 dB, which is highly significant. So this was a huge success. So some of the conclusions, the paper targeted a different approach for the design of the suction muffler, and we saw that the rigid wall approach for polymeric muffler was highly ineffective, but FSI approach was really much better and represented better the problem, which gave more realistic results, and the heuristic optimization was much more effective at tuning into the cavity bands. So thank you very much, and we are open for questions. If you have questions, doubts, or if you want to share any thoughts, this is it. Thank you very much.
Thank you, Paulo. Interesting topic, interesting presentation. I don't know if we have any. Yes, we have the first question here. When using can you see this on the screen so you can read by yourself? Approach better results when about computational time and model setup time when comparing with the rigid wall approach. Did you hear my question? I think, Paulo, you have to unmute yourself. You are muted, Paulo. Can you hear me? Paulo, you disappear from the connection
problem.
So I think he will reconnect. Let's. So let's see if he will join back the. I have one question to the host. Do we have the last presentation?
Yes, we do.
Presenter? Yeah, okay. Because seems not connected. So how about the timing? We are on time. We can wait a little, or we have to start the next one.
Actually, looking again, we don't have the presentation by Professor Bajdak. So if he's not present, then this is the end of the session.
Yeah. So let's wait a few minutes to if maybe one or two questions. Because I had the same problem. I was disconnected automatically when Paulo was speaking, so I have to reconnect again. So we have 3 questions, but there's no Paulo to answer to them. Okay, so at this point, I would say that we can close the session. Correct, Tiago?
Yeah, because I don't know if we should wait a little bit more, but he had time, I think, to reconnect. Yeah. Otherwise, maybe something happened. We don't know what exactly. Mm-hmm. But I agree with you, because since we do not have a Professor Bajdak presentation, and we do, unless we have also remaining questions regarding the first 2 presentations, if anybody wants to ask anything else, but if they don't, I agree with you, and we should close the session.
Yeah. So let's see. there was a question to Asmund related to his presentation about valve. Can the models be adapted for valve types used in small compressors? So this was a question.
Yeah, so I assume that the person asking the question is thinking about reed valves or something along these lines. So I would say yes, it can be adopted, but it is of course a very different geometry. So you need to first of all discretize this geometry and then to implement the spring forces in that type of system, which are part of the solid itself that is deforming and not explicit springs.
Mm-hmm.
So I would say it's possible, but there is quite some work
to be done. Yeah, I understand. And there's another question, as always to you. Question: is the methodology used on two-way FSI or one-way FSI?
And so I would say the approach presented in the paper is one-way FSI, and we are currently working on two-way FSI.
Mm-hmm. Okay. So there is a question, you can read it. So about the computing time and model setup.
I think this was a question for
for
Paulo.
for Paolo.
Paolo, yeah. Sorry. Yeah, okay. So since we cannot see Paolo, I think we can close the session. Thank you very much to the authors and to the audience attending this presentation, and I think we will be all connected for the closure of the conference at 5 p.m. European time. That will be 11 a.m. for me. Thank you again. Thank you, Tiago, for co-chairing this session. And I hope to see you all in the next Slovakian Compressor Conference in person in Slovakia. Okay. Thank you very much and have a nice day.
Thank you.
Thank you.